Chapter 1. The Carbon Prison. In the black mirror of a dilated pupil, what reflects back isn't just a starry sky. It is an abyss that stares right back at us. Cold light from distant galaxies falls upon the warm, wet surface of an eye. The most perfect instrument biological evolution has crafted over 4 billion years. But this very instrument, fine-tuned to search for familiar shapes and colors, has become our greatest trap. We look out at the universe expecting to see our own reflection, but the cosmos isn't obligated to mirror us back. The rapid ascent through Earth's dense atmospheric layers strips away the veil of clouds, revealing the true scale of our solitude. The stratosphere gives way to vacuum, and Earth becomes a pale blue dot dissolving into infinite darkness. Here in orbit, the fragility of our watery cradle becomes obvious. We've grown accustomed to thinking of this blue color as the symbol of life, the only possible marker of habitability. But to an outside observer with a different biochemistry, our planet might appear toxic, oxidized, unfit for existence. The landscape shifts to Mars's lifeless, rust-colored deserts. Dust storms polish rocks that have remained silent for millions of years. We send rovers here equipped with detectors, calibrated to search for water and organic compounds. We look for traces that resemble our own, and when we don't find them, we diagnose the planet as dead. This verdict, though, rests on a dangerous assumption that life is the exclusive privilege of protein-based bodies requiring oxygen and comfortable temperatures. The foundation of our biological arrogance rests on 6 chemical elements. 98% of Earth's biomass, from microscopic bacteria to blue whales, consists of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. This sacred 6 has become our dogma. We've grown so accustomed to the carbon framework of our cells that we deny the universe the right to experiment with different matter. We confuse the familiar with the only possible. In 1973, astrophysicist Carl Sagan found the perfect term for this scientific myopia. He called it carbon chauvinism, the belief that biological processes throughout the universe must copy Earth's script. Sagan warned, by limiting our searches to carbon and water alone, we risk walking past civilizations that breathe stone or think in plasma clouds, simply because our instruments wouldn't recognize them as alive. Let's slow down here. The statistics work against our claim to uniqueness. Current estimates suggest there are up to 2 trillion galaxies in the observable universe. Each contains hundreds of billions of stars and planetary systems, with conditions we can barely imagine. To assume that in this gigantic chemical factory, nature used only one recipe, Earth's recipe, isn't just naive. It is statistical madness that contradicts the very logic of probability. Data from the James Webb Space Telescope in 2024 reveals exoplanets, where molten iron falls as rain and clouds consist of silicates. Chemistry there operates under laws extreme to us, but perfectly normal for the local environment. In these hellish cauldrons, molecules might assemble into structures rivaling DNA in complexity, but possessing fundamentally different architecture. What we call deadly conditions might be someone else's perfect resort. Chapter 2. Silicon's Failure on Earth. To test our bold hypothesis about alternative life, we must leave open space and descend into a laboratory's sterile silence. Here, under fluorescent lights, an astrochemist looks at the periodic table not as a list of elements, but as a map of family relationships. His attention focuses on the 14th group, right here, directly below carbon. The basis of our flesh sits its closest chemical relative, silicon, to the untrained eye. These two elements seem like complete opposites. In the researcher's left hand, a piece of black graphite, soft and staining to the touch. In his right, a transparent quartz crystal, hard and cold. But viewed through an electron microscope, the differences disappear. Both carbon and silicon possess a rare gift that chemists call a valence of 4. This means each of their atoms has 4 free hands to grab other atoms. It is precisely this ability to create 4 bonds simultaneously that allows the construction of the most complex 3-dimensional structures necessary for life. And here is where we encounter the main paradox that haunts scientists. Earth's crust is almost 30% silicon, literally dirt under our feet. Carbon, meanwhile, makes up pathetic hundredths of a percent of the crust. Statistically, life on Earth should have chosen silicon. There was thousands of times more building material available. Why did nature ignore mountains of construction material and choose rare, scarce carbon instead? The answer lies in the strength of the foundation. The astrochemist runs a simulation of molecular chains. Carbon easily bonds with itself, forming infinitely long and sturdy backbones for proteins and DNA. The carbon-carbon bond is the steel cable of the microcosm, strong enough not to disintegrate spontaneously, yet flexible enough to permit reactions. With silicon, the situation changes dramatically. As soon as a chain of silicon atoms becomes longer than about 10 links, it begins behaving unstably. The silicon bond energy is half that of its carbon equivalent. For a laboratory observer, this looks like catastrophe. A complex molecule that could become the basis for an alien genome crumbles under its own weight. At the slightest external influence, water makes things worse. We consider water life's cradle, but for silicon structures, it is aggressive acid. Water molecules attack weak silicon bonds, breaking them through hydrolysis. Under Earth's warm, humid conditions, silicon-based life would be doomed to instant decomposition. Any attempt at evolution would be washed away by the first rain, turning a complex organism into a puddle of silicate gel. But the most fatal problem lies not in the skeleton, but in breathing. Life is a constant process of oxidation. We burn fuel to get energy. When carbon combines with oxygen, carbon dioxide is born. This volatile substance easily leaves the cell and gets eliminated from the organism. We exhale the waste products of our metabolism effortlessly, dissolving them into the atmosphere. The astrochemist conducts a simple experiment. He heats graphite, and it disappears, transforming into invisible gas. Then he tries the same with silicon. The result of silicon oxidation is silicon dioxide. Not a gas, but a solid crystalline substance we know as sand or quartz. This is a thermodynamic death sentence. If you were a silicon-based creature on Earth, every exhalation would mean creating solid rock inside your lungs. Imagine an organism that breathes out bricks instead of air. Eliminating solid breathing waste would require colossal energy expenditure, making biological existence unprofitable. That is exactly why silicon on Earth chose the path of least resistance, freezing into dead rocks and sand. Under our conditions, our pressure and temperature, silicon lost the evolutionary race to lighter, more flexible carbon. Biochemists long considered these facts the final verdict. Silicon is too weak, its bonds break from water, and its breathing creates stones. Case closed. Not quite. Chapter 3. The Water Problem. We've been blaming silicon for the absence of silicon-based life. In the previous chapter, we established its weaknesses: bonds too fragile, breathing products too solid. But this verdict holds only as long as we consider it in the context of Earth conditions. Perhaps the problem isn't with the actor, but with the stage we're trying to bring him onto. And the main culprit here might be a substance you consider synonymous with life itself. Water. In our consciousness, water is life's universal cradle, soft and life-giving. But from chemistry's perspective, water is an aggressive polar solvent that behaves like a molecular vandal. For carbon, it serves as an ideal reaction medium, but for silicon, water is acid that slowly and methodically destroys any attempts to create complex structure. Look at a computer simulation of ancient Earth. We've removed familiar biological algorithms and observe atomic behavior at the nanoscale. You see silicon atoms trying to build long chains, the foundation for future DNA or proteins. But as soon as this chain forms, water molecules, wielding powerful electric dipoles, attack the connection points between atoms. This process is called hydrolysis. Water literally cuts silicon bonds, wedging itself between them and turning a promising molecule into a heap of simple oxides. The bond energy between silicon atoms is half that of carbon. In an aqueous environment, they simply have no chance against the solvent's chemical aggression. On Earth, water prevents silicon from evolving, forcing it to oxidize into inert sand. This brings us to a paradoxical conclusion. Earth is unsuitable for silicon life precisely because it is too good for carbon life. Our oceans are poison to alternative biochemistry. Therefore, searching for silicon-based brothers in the so-called habitable zone, where water remains liquid, means searching exclusively for carbon analogs of ourselves. We're looking for a mirror while ignoring the rest of reality. To give silicon a chance, we must radically change our simulation parameters. We need to remove water or freeze it into rock so it stops being an active chemical agent. But life can't exist in dry form. It needs a liquid medium for transporting materials. If we remove water, what takes its place? Science offers us a list of alternative solvents capable of supporting life. The first candidate is extreme and frightening: sulfuric acid. Under certain conditions different from Earth's, it can support much more complex chemical reactions than water. Thanks to its wide temperature range in liquid state, sulfuric acid can create a stable environment for molecules that would decompose in fractions of a second on Earth. But for silicon, there is a more elegant solution. We must turn our gaze toward cold, where thermodynamic chaos quiets down. Under low temperatures, chemical activity slows, and silicon's weak bonds, which broke in Earth's heat, gain unexpected strength. In this cold world, methane takes water's place. In the temperature range from -182 to -161 degrees Celsius, methane transitions to liquid state. This isn't just compressed gas. It is a full solvent resembling water in properties, but lacking its aggressive polarity. In liquid methane, hydrolysis is impossible. For a silicon molecule, this is a safe harbor. Let's return to our simulation. We lower the temperature to -180 degrees Celsius and replace the virtual water ocean with a methane ocean. The picture changes instantly. Water here has turned to ice, hard as granite, and become part of geology, not biology. Silicon chains, previously torn by hydrolysis, now drift peacefully in the methane environment, maintaining their integrity. Under such conditions, silicon's bond weakness becomes its advantage. At ultra-low temperatures, rigid carbon bonds would become too inert, frozen, incapable of reactions. But more labile, flexible silicon bonds retain the ability to restructure and interact. What was a disadvantage in heat becomes a survival condition in cold. Of course, life in a methane ocean would differ from ours. Chemical reaction speeds there are thousands of times slower. A creature living in such a world would need years to make a movement that takes you a second. But time in the universe is an unlimited resource. For an observer from a methane planet, our frenetic carbon life would seem like an explosion, a flash that burns too quickly. This makes us reconsider the very definition of habitability. We consider Earth the norm, but perhaps our planet, with its hot oxygen fires and aggressive solvent, is a rare, dangerous anomaly. Cold worlds filled with hydrocarbons and ammonia might be the statistical standard for the galaxy. We've theoretically proven silicon life is possible if we find it the right home. A home where water is solid as rock, where natural gas rains from the sky, and rivers flow slowly and viscously. The most amazing thing? We don't need to fly to another galaxy to find such a place. It exists right here in our solar system, waiting for our visit. This world orbits Saturn, hidden beneath dense orange haze. It is Titan, the only place in our system besides Earth where stable liquid exists on the surface. But it is not water. It is that same liquid methane we just observed in our simulation. Time to test our theories against practice and look at the shores of seas where entirely different life might be emerging. Chapter 4. Titan's Methane Seas. Silence in mission control seems denser than the atmosphere our probe is now penetrating. For the operator sitting before a wall of monitors, the distance of 1.5 billion kilometers translates into agonizing 80-minute signal delays. We're no longer in theoretical chemistry territory. We're entering the realm of real physics, where formulas from the previous chapter acquire substance. Here, in Saturn's system, the hypothesis about methane solvents faces its harshest test with reality. On telemetry screens, dense orange haze emerges through interference. This is Titan, the only celestial body in our solar system besides Earth, possessing a full, thick atmosphere. Surface pressure here equals 1.5 Earth atmospheres. If you stood there, you wouldn't feel the need for a pressure-compensating spacesuit, just an oxygen mask and a very warm coat. The operator watches the altitude graph plummet. The Huygens probe sheds its heat shield and deploys parachutes. What the descending spacecraft's cameras reveal causes cognitive dissonance among scientists. It looks frighteningly familiar. We see riverbeds, winding coastlines, smooth lake surfaces, and even dunes resembling Namibian deserts. This world's geology painfully resembles Earth's, but it is a deception, a deadly trap for the unprepared mind. Here, every familiar object consists of completely alien materials. This is Earth's twin, turned inside out by cosmic cold. The mountains radar detects aren't made of silicate rocks. They're water ice. At -179 degrees Celsius, water loses all resemblance to the liquid we know. Here it is, harder than granite, serving as bedrock, tectonic plates, and stones underfoot. Water on Titan is dead matter, construction debris that never melts. For local chemistry, it is as inert as ordinary boulders are to us. But if water is stone, what flows in these rivers? Spectral analysis data from the Cassini mission confirmed what we discussed earlier. Liquid methane plays water's role here. A mixture of methane, ethane, and dissolved nitrogen undergoes a complete cycle, evaporating, condensing into clouds, and falling as rain. Only these rains fall slowly, dreamlike, due to low gravity, and droplets reach grape size. The operator changes image filters, focusing on polar regions. There lies Kraken Mare, a giant reservoir of liquid hydrocarbons. By area, it exceeds our Caspian Sea, spanning 400,000 square kilometers. This isn't just chemical puddles. It is a full ocean with currents, tides, and most importantly for us, gigantic potential for dissolving complex molecules. Remember silicon's problem we discussed. Water destroys its bonds, oxidizing it to sand. But here, in Kraken Mare, there is no aggressive oxygen and no liquid water. The environment that would kill an Earth bacterium in fractions of a second is paradise for silicon structures. Liquid methane is a neutral solvent. It doesn't attack molecular chains, allowing them to grow, complexify, and form structures impossible on warm Earth. Titan's atmosphere works like a gigantic chemical reactor. Solar ultraviolet and particles from Saturn's magnetosphere bombard methane and nitrogen molecules in the upper layers. This produces tallins, complex organic compounds that slowly settle on the surface as orange snow. It is manna from heaven for a potential biosphere. Hugh carbon and hydrogen reserves, ready building blocks for life, literally falling from the sky. But having building blocks isn't enough. Energy is needed. Here, skeptics point to Titan's main disadvantage: cold. At minus 180 degrees Celsius, chemical reactions slow almost to a complete stop. What takes milliseconds on Earth might last centuries here. But let's view this through an astrophysicist's eyes, not a biologist's. Time is relative. If your life lasts millions of years, slow metabolism isn't a problem. Besides, we judge by Earth's activity standards. We seek thermal energy, but Titan might operate on a different principle. Chemical gradients, for example. Acetylene hydrogenation. Acetylene falling from the sky reacts with hydrogen at the surface, releasing energy. This could be analogous to our breathing. Consuming acetylene, exhaling methane, probe data shows a strange anomaly. Hydrogen concentration at the surface is lower than calculated, as if someone or something actively consumes it. Imagine this world, dark, lit only by distant sun's dim light and Saturn's reflection. The surface crunches under landing supports. This is a crust of hydrocarbons, hiding liquid mud beneath. Around is silence, broken only by methane wind noise. But this silence is deceptive. Hidden within it is colossal potential for matter organization. Thermodynamic laws work here as everywhere else. Entropy must grow, and life is a way to accelerate this growth through energy dissipation. We've grown accustomed to thinking the habitable zone is a narrow strip around a star where water remains liquid. Titan shatters this concept. It proves a second habitable zone exists, the liquid methane zone. If we're right, there are orders of magnitude more such worlds in the universe than Earth analogs. Cold super-Earths, icy giant moons, all could be cradles for life that considers our room temperature deadly hellish heat. The operator records data from tilt sensors. The probe rocks slightly. Perhaps it is just dense wind, or maybe liquid movement beneath the surface. We look at these lakes and don't see familiar waves, because methane's viscosity differs. This is an oily, viscous environment, perfect for forming membranes that don't dissolve but function as protective shells for internal metabolism. We approach the limits of our camera's capabilities. We see the landscape, know the chemical composition, understand the physics, but we don't see the main thing. What happens at the microscopic level in the depths of these oily waters? What might a cell living in gasoline look like? It can't have the familiar lipid shell in methane. Our membranes would simply turn inside out and disintegrate. To peer deeper, we must leave the control room and return to models, because nature, as it turns out, has found an elegant solution to this problem too. A solution allowing cell creation without a single drop of water, using substances we use on Earth for synthetic fabric production. Titan has prepared the stage, arranged the scenery, turned on the lighting. What remains is seeing the actors. Chapter 5. Azotosomes. Cells without water. We plunge into Kraken Mare, not with a camera, but with a supercomputer capable of calculating this alien world's molecular dynamics. The answer to Titan life's mystery lies not in ice mountains, but in tiny bubbles invisible to the eye, drifting in darkness. This isn't science fiction, it is rigorous calculation. If life exists there, this is exactly how it must look. Diving into Kraken Mare changes perception of reality itself. Here, at depths, where pressure exceeds Earth's by 1.5 times, absolute viscous darkness reigns. To your eye, this liquid would seem unnaturally calm. Liquid natural gas dampens oscillations differently than water. An astrochemist viewing molecular scanning data sees here not just a fuel reservoir, but a giant vat of prebiotic soup. But for this soup to become life, it needs a container, a boundary, separating self from non-self. On Earth, phospholipid membranes create this boundary. This brilliant natural invention works on one principle. Molecules have heads that love water and tails that fear it. In water, they automatically assemble into bubbles, hiding tails inside. But here, in a methane ocean, Earth biology faces a fatal problem. Methane isn't a polar solvent. It doesn't repel fats, it dissolves them. An ordinary Earth cell would disappear instantly in this sea, like ink dissolving in a glass of water. Its shell would simply cease to exist. This means Titan life must be turned inside out. Literally. Evolution's chemical engineers must create an anti-membrane. Its outer side must be non-polar to interact with methane, while the inner side stays polar to maintain an isolated environment for metabolism. It was long believed such structure was chemically unstable at -179 degrees Celsius. Cold was thought to make any membranes too rigid, brittle, incapable of division and substance transport. The breakthrough came in 2015, when Cornell University researchers, using powerful supercomputers, modeled various molecules' behavior in cryogenic methane. They sought structure that would retain flexibility and strength under these hellish conditions. And they found it. The calculation result got the name azotosome, a hypothetical analog of our liposome, built not from phosphorus and oxygen, but from nitrogen, carbon, and hydrogen. This discovery overturned century-old biological dogma. The key component of this alien flesh is acrylonitrile. On Earth, you know this substance as a toxic reagent for producing acrylic fabrics and plastics. Our laboratories work with it in protective suits, but for an astrochemist studying Titan, acrylonitrile isn't poison, it is life's building block. Modeling showed this substance's molecules in liquid methane can self-organize into durable, elastic spheres. They create bubbles that don't freeze or crack, even under conditions where steel becomes brittle as glass. Skeptics might object that computer modeling is just number games, but data from the ULMA telescope array in Chile's Atacama Desert confirmed massive acrylonitrile presence in Titan's atmosphere. Spectral analysis shows this gas constantly forms in upper layers under solar ultraviolet and falls as plastic snow on the surface, saturating lakes with necessary building material. Life's ingredients don't just exist, they literally fall from the sky. Imagine what an astrochemist sees looking at this data. Not a poisonous ocean, but perfect assembly environment. Azotosomes are elegant entropy solutions. Acrylonitrile membranes possess flexibility comparable to Earth organisms' cell membranes. This allows potential Titan inhabitants to change shape, absorb nutrients, and possibly even divide. These aren't frozen crystals. They're dynamic soft matter capable of complex biological maneuvers. But biochemistry at such temperatures dictates its harsh time rules. All chemical reactions slow geometrically. Titan creatures' metabolism must be tens of thousands of times slower than ours. For a real-time observer, these azotosome jellyfish would seem motionless statues. Their heartbeat, if we can apply such a term to chemical cycles, would happen once every few hours, and nerve impulse transmission would take minutes. But for them, this would be normal existence rhythm. This time factor changes evolution's very concept. If Earth took billions of years to go from simple cells to humans on Titan due to slowed metabolism, an analogous process might take time exceeding the universe's current age. Or perhaps they found catalysts we don't know about. Maybe they have enzymes capable of accelerating reactions in liquid methane as efficiently as our proteins do in water. Visually, these organisms would be almost invisible to human eyes. Acrylonitrile membranes are transparent, and their internal environment's refractive index is close to surrounding methane. Only in ultraviolet spectrum or with special lighting would you notice ghostly drifting spheres ranging from microns to several centimeters. They don't need rigid skeletons since dense liquid supports their structure, allowing creation of bizarre colonies resembling earth sponges or corals, but consisting of living plastic. These creatures' breathing poses another puzzle we must solve. Without oxygen, they might obtain energy by reacting hydrogen with acetylene, converting it to methane. This process, called hydrogenation, theoretically releases enough energy to sustain life. Curiously, the Huygens probe detected anomalous hydrogen concentration decrease at the surface upon landing, as if someone or something actively consumes it. Thus, Titan offers us biology's alternative version, waterless, cold, slow, built on nitrogen and hydrocarbons. It is mirror Earth, where everything familiar is replaced by alien analogs. But function remains the same: fighting chaos, organizing matter, life. Azotosomes prove nature isn't limited by rules written for a warm, watery planet. She uses whatever physics laws are available at any specific space point. We've grown accustomed to seeking water, considering it all life's cradle. But Titan teaches us the cradle can be liquefied gas. If we're right, and billions of invisible sluggish creatures drift in Kraken Mare, this means the universe is filled with life much denser than we dared hope. Cold hydrocarbon worlds vastly outnumber warm water oases. We're the rare exception, they're the standard. Chapter 6. Venus. Life in acid clouds. But cold is just one extreme on the scale. If life can adapt to temperatures where air becomes liquid, can it survive where lead melts like wax? We leave the icy wastelands of the outer solar system and head to the inner boundary of the habitable zone, where chemistry transitions into fire's alchemy, and where the very concept of organic molecule seems like physics' mockery. We leave Titan's cryogenic methane rivers behind, and telemetry change hits the eyes with a sharp readings jump. The temperature graph on the probe operator's monitor rockets vertically upward, breaking the 460 degrees Celsius mark. We're approaching Earth's evil twin, Venus. If Titan was cold's kingdom, preserving prebiotic soup in deep freeze, here hellish sterilization reigns. For an observer monitoring data flow, this planet's surface looks like any organic matter's death sentence. Pressure of 90 atmospheres could crush nuclear submarines, and heat melting lead turns landscape into sterile basalt desert. Searching for life here might seem like madness bordering on space mission budget waste. But the operator knows to look not down at scorching stones, but up. At 50 kilometers above surface, sensors detect an anomalous calm zone. Here, among dense clouds, temperature drops to comfortable 30 degrees Celsius, and pressure equalizes to 1 Earth atmosphere. This is the so-called Goldilocks zone, a layer where physical conditions nearly match an Earth resort. The only problem, these clouds' composition. This isn't water vapor, but concentrated sulfuric acid. In September 2020, the scientific world was shaken by news from James Clerk Maxwell and ALMA telescopes. Venus atmosphere spectral analysis showed a molecule that shouldn't be there. On the operator's graph, this peak looks like tiny but distinct dip in the spectrum line at 1.123 millimeters wavelength. This is phosphene's signature. For an astrochemist, discovering phosphine on a rocky planet equals finding smoke in a closed room. These molecules consist of 1 phosphorus atom and 3 hydrogen atoms. In atmosphere saturated with oxygen or sulfur, phosphine should instantly oxidize and decompose. Its constant presence means only one thing: someone or something continuously replenishes its supplies. On Earth, anaerobic bacteria are phosphine's only producers. Skeptics immediately proposed dozens of hypotheses, from unknown photochemistry to volcanic activity. But calculations show no geological process can produce phosphine on such industrial scales. We face a dilemma. Either we've discovered completely new unknown chemistry, or a gigantic biosphere floats in Venus's poisonous clouds. But the very idea of life in this environment seems absurd to biological minds. Venus clouds consist of sulfuric acid droplets with 85 to 90% concentration. For comparison, carbattery acid has about 30% concentration and can dissolve tissue. Earth biochemistry, based on DNA and proteins, would decompose to atoms in fractions of a second under such conditions. Here we again encounter carbon chauvinism. We judge survivability by our standards. But what if Venusian life uses sulfuric acid like we use water? Calculations show complex polymers unavailable in aqueous environments might exist in this aggressive liquid. Sulfur's role here might be played by stable 8 atom sulfur rings, known as cycloctasulfur. Look at hypothetical modeling data. These creatures aren't bacteria in our understanding. They're microscopic living droplets protected by graphite or sulfur polymer shells. They live inside acid aerosols, extracting energy from sunlight and sulfur chemical reactions. They never touch the surface. Their entire life cycle happens in eternal flight. Their main threat is gravity. If a droplet becomes too heavy, it starts falling into atmosphere is lower layers, where temperature evaporates everything. Scientists propose a complex life cycle existence. Drying spores fall down into the inferno, where they enter suspended animation, while rising thermal currents return them to the cool zone, where they rehydrate with acid and revive. This hypothesis overturns our habitable zone concepts. We've grown accustomed to seeking liquid water on planetary surfaces. But Venus proves a planet can be dead outside, but alive inside its atmosphere. The biosphere can be not a film on stone, but a three-dimensional volume, a cloud ocean drifting above a scorching pan. Phosphene's discovery, even if disputed in the future, has already accomplished the main thing. It forced us to reconsider chemical maps. We understood life isn't necessarily bags of salted water. Life can be acid resistant, using aggressive solvents as protective environments from competitors and predators. For them, water would be as poisonous as sulfuric acid is for us. The probe operator continues scanning the spectrum, and each new data byte only intensifies suspicion. We're not alone in the solar system. Our neighbors simply chose apartments with conditions we consider unsuitable for existence. We sought mirrors and found alien, incomprehensible chemistry thriving under absolute toxicity conditions. But if life can hide in Venus clouds and Titan's methane lakes, if it can use sulfur and methane instead of water and carbon, a frightening question arises. Are we sure we've found all life on our own planet? How perfect are our detection methods if they're calibrated only to search for familiar proteins and nucleic acids? Perhaps the aliens we so persistently seek in space are right here, under our feet, in hot springs, salt deserts, or even on laboratory benches. We simply don't see them because our science is blind to everything not fitting carbon biology dogma. Time to return to Earth and look at it with alien eyes. Chapter 7. Earth's Shadow Biosphere. After Venus's hellish temperatures and Titan's icy silence, returning to Earth feels like salvation. But an astrochemist standing in the world's driest desert, Atacama, doesn't feel at home. For him, this landscape is equally alien territory. Beneath his feet crunches not just sand but oversalted crust, burned by ultraviolet. Here, in a place biologists call the Martian testing ground, we must ask ourselves an uncomfortable question. Do we really know all inhabitants of our own planet? We've grown accustomed to thinking Earth life is a single tree with common roots, from amoebas to humans. We're all connected by one biochemical architecture: DNA, RNA, proteins. But what if this tree isn't the only one? In the researchers' hands, an ordinary-looking rock covered with strange dark film. This is desert varnish. Geologists have known about it for centuries. A thin layer of manganese and clay that accumulates over millennia. But no one knows exactly how it forms. From an astrochemist's perspective, this dark coating is a glaring anomaly. Manganese concentration in the varnish is 50 times higher than in surrounding rock. Chemistry alone doesn't create such gradients. This is living organisms' work. But when scientists try taking scrapings for DNA analysis, results often turn up empty or incoherent. We see life activity traces, we see chemical work, but don't see the worker himself, as if someone invisible builds castles from dust under our feet. Here we encounter modern science's fundamental problem: our main life, searching tools, polymerase chain reaction, PCR, and genome sequencing, are calibrated very narrowly. They work like search radar, looking only for specific frequencies. If an organism lacks ribosomal RNA, or its genetic code is written on a different molecular basis, it simply doesn't exist for our instruments. We look through microscopes but see only what we already know. This blindness is exactly what the shadow biosphere hypothesis describes, proposed by science philosopher Carol Cleland and colleagues. The idea's essence is frighteningly simple. Earth life might not have originated just once. In the primordial soup 4 billion years ago, different life forms might have emerged. One branch, ours, carbon protein, based, captured resources, and became dominant. But this doesn't mean others disappeared. They might have gone into shadow, occupying niches inaccessible or uninteresting to us. Imagine microorganisms for whom oxygen is poisonous, or those using arsenic instead of phosphorus in structural elements. They don't compete with us for food, don't cause diseases, so our immune system doesn't notice them, and science ignores them. The shadow biosphere might exist literally on this rock surface in Atacama, feeding on rare minerals. We continue considering this rock lifeless simply because our DNA test gave negative results. To understand how extreme even known life can be, the astrochemist turns to proven facts. A bacterium exists that already breaks our conception of possibility. D. Oinococcus radiodurans. Scientists jokingly call it Conan bacteria. If lethal radiation dose for humans is about 5 grays, this microorganism calmly withstands 5,000 grays. Radiation capable of boiling water in cells and tearing any known protein structure. At 5,000 grays, ordinary organisms' DNA becomes useless chemical debris sets. DNA tears into hundreds of small fragments. But Deinococcus radiodurans possesses unique repair mechanisms. Within hours, it reassembles its chromosome from pieces without errors or mutations. This suggests, if familiar protein life can achieve such survival feats, what might shadow biosphere representatives, whose chemistry might be initially more stable, be capable of? The shadow biosphere hypothesis proposes we live in a world of microbial dark matter. Microbiologists estimate that modern methods cultivate less than 1% of all microorganisms living on Earth in laboratories. 99% of planetary biodiversity is unknown to us. We simply can't select conditions for them because we don't know what they eat or breathe. Perhaps part of this unknown percentage is exactly those aliens we seek on Mars. The astrochemist looks at the barren desert and sees not emptiness, but hidden overpopulation. If shadow life exists, it might use molecular mirror chirality. So, called right amino acids instead of left ones that all our biology uses. Ordinary bacteria enzymes can't break down mirror molecules, meaning the shadow biosphere is invisible to standard world predators. This is perfect camouflage. Being made from matter no one can digest. Accepting possible shadow biosphere existence requires intellectual humility. We must acknowledge Earth isn't only our planet. We, carbon-based life on aqueous foundation, are possibly just the noisiest and most visible tenants in this dormitory, but not the only ones. Right now, structures living by completely different physical laws might exist on your skin or in a water glass, and we're just background noise, geological environment to them. But science doesn't tolerate uncertainty. Hypotheses remain hypotheses until we catch a shadow microbe by the tail. But how do you catch someone who passes through all our filters? The answer is paradoxical. If we can't find alternative life in nature, we must try creating it ourselves. We need to reproduce evolution's conditions and see if matter can find another path besides the one Earth biology chose. This is where observation ends and experiment begins. Chapter 8. Creating Silicon Life in the Lab. We leave scorched deserts and enter California Institute of Technology's sterile zone. Here, under cold lamplight, where air smells of ozone and alcohol, silence is broken only by robotic manipulators' rhythmic humming. The astrochemist views this process not as creating Frankenstein monsters, but as correcting historical injustice. Earth nature has separated carbon and silicon with an impenetrable wall, but here, in this reactor, we intend to tear down this wall. In our planet's natural environment, carbon and silicon are periodic table neighbors who practically don't communicate. Carbon builds flesh, silicon builds stones. In nature, not one known enzymatic reaction connects these two elements in living cells. This seems like biology's fundamental prohibition, but our astrochemist knows what nature didn't do doesn't mean she can't do it. She simply lacked motivation or time. Biology certainly knows how to work with silicon. Ocean diatoms annually extract billions of tons of dissolved silicon from water to build their incredibly complex, geometrically perfect shells. But this is exoskeleton, armor. This is house construction, not bodybuilding. Inside diatoms, the same old carbon machinery still operates. The task before laboratory scientists is far more ambitious. Force life to let silicon inside its metabolism. The tool used for this hack is called directed evolution, a method that earned the Nobel Prize. Its essence is simple and brutal. We take a natural protein and force it to mutate in a test tube, creating thousands of random versions. Then we select only those performing the assigned task better than others and repeat the cycle. What takes natural selection millions of years happens here, thanks to robots, in days. Cytochrome C, taken from bacteria living in Iceland's hot springs, was chosen as the test subject. This enzyme naturally handles electron transfer, but it has hidden potential. Scientists hypothesized its structure was flexible enough that certain mutations could make it begin catalyzing carbon, silicon bond formation. This was betting on biology's hidden reserves that nature herself might have forgotten. First experiment iterations gave weak results. Enzymes worked slowly, reluctantly, often breaking down. But with each directed evolution generation, with each new test tube the robot manipulator sent to the analyzer, efficiency grew. The astrochemist sees on the monitor screen how protein three-dimensional structure changes. Several point mutations in genetic code altered the enzyme's active center shape, turning it into a specialized silicon working tool. In 2016, this barrier finally fell. Researchers obtained modified enzyme that actively began stitching carbon and silicon atoms together, creating organic silicon containing molecules. This isn't just chemical reaction, it is biological synthesis. Bacteria began producing compounds that until that moment existed only in synthetic chemistry textbooks, doing so inside their cells without dying. Results stunned the scientific community. The obtained mutant enzyme created carbon-silicon bonds 15 times more efficiently than the best human, made catalysts created under factory conditions. Moreover, the biological process proved surprisingly clean, requiring no toxic solvents or extreme temperatures. Life, given proper instructions, surpassed industrial chemistry on its first serious attempt. For the astrochemist, this monitor graph represents not just experimental success, but paradigm shift. We proved Earth biology has no chemical allergy to silicon. Cellular mechanisms can fully integrate this element into their structures. The fact that we don't consist of silicon isn't a physical prohibition, but historical accident. Early Earth simply had carbon slightly more accessible and energy efficient as a solution. Now imagine a planet with slightly different conditions, where there is more silicon and less carbon, or where absent oxygen doesn't allow carbon oxidation to carbon dioxide. The Caltech experiment proves, put evolution in such conditions, and it will inevitably find a path to silicon life. It doesn't need to reinvent the wheel. Just slightly modify existing tools like cytochrome C, we've actually created hybrid life right here in Pasadena. These bacteria are first citizens of a new silicon, carbon biosphere. Looking at a test tube with cloudy liquid, we see not just microbial colony, but proof of concept. If we accomplished this in a couple years in one laboratory, what could the universe create over 13.8 billion years in countless galactic chemical cauldrons? This experiment erases boundaries between living and non-living, between biology and mineralogy. We've grown accustomed to thinking rocks are dead and proteins are alive. But we forced proteins to work with stone as if it were their native environment. This discovery forces us to reconsider life's very definition. Life isn't the material it is made from. Life is information that subjugates matter, whether carbon, silicon, or something even more exotic. But even in this bold experiment, we're still tied to substance. We talk about atoms, molecules, chemical bonds. We still think in categories of solids and liquids, but the universe is 99% not solid matter, but ionized gas, plasma. Can mind exist where there is neither carbon nor silicon, but only pure energy and electric fields? To answer this question, we must leave Earth's cozy laboratory and rise to orbit, where vacuum and radiation create conditions impossible on planetary surfaces. Chapter 9. Plasma Crystals. Life from Pure Energy. The team is here, 400 kilometers above Earth's surface, inside the International Space Station's laboratory module. The plasma physicist looks through the porthole not for beautiful views, but to calibrate instruments against cosmic vacuum background. Before him lies a sealed vacuum chamber where the fourth state of matter reigns, plasma, ionized gas from which stars and interstellar nebulae consist. But now the researcher's interested, not in the gas itself, but in ordinary microscopic dust introduced into this chamber. Under Earth's gravity, these dust particles would simply fall to the bottom. But here, in microgravity, under powerful electric field's influence, something happens that violates intuitive chaos understanding. Instead of flying apart chaotically, particles begin sensing each other. The physicist sees them arrange in strict, almost military order, forming a levitating crystalline lattice. This is a plasma crystal. But the most stunning discovery awaits when he changes laser radiation parameters. The structure begins behaving not like a mineral, but like a living creature. The physicist observes dust particles twisting into spirals. You look at the monitor and see a form painfully familiar to every schoolchild. A double helix identical to DNA structure. Only this helix consists not of nucleotides, sugar, and phosphates, but of solid microparticles held by electric charge. This discovery by Russian scientists forces us to completely reconsider boundaries between physics and biology. In 2007, a group of scientists led by Professor Vadim Saidovich from the Russian Academy of Sciences General Physics Institute published sensational data. They proved that under certain conditions, inorganic dust particles in plasma self-organize into complex spiral structures. This isn't coincidence or optical illusion. It is a new form of matter displaying properties previously attributed exclusively to biological life. These spirals don't just hang in vacuum, they feed. The structure absorbs plasma ions from surrounding environment, creating flows around itself analogous to metabolic processes in living cells. They convert chaotic plasma motion energy into energy for maintaining their own ordered structure. From thermodynamics perspective, this is life's main definition: local entropy victory through external energy consumption, But Seidovich's group discovery goes further. These plasma crystals can reproduce. When a spiral accumulates critical mass and becomes unstable, it divides into two identical copies. Moreover, these copies inherit the maternal spiral structure. This means they have primitive genetic memory without any chemistry. Information transfers not through molecules, but through electric field geometry. You observe real evolution in vacuum. Different spirals compete for plasma flows. Essentially, food structures with more stable geometry survive and leave offspring. Weaker ones decompose back into dust chaos. This is Darwinian natural selection, requiring neither water nor carbon nor sunlight. Only dust, electricity, and vacuum. We've grown accustomed to seeking life on planets, but what if we're ignoring the very emptiness between them? 99% of visible matter in the universe exists in plasma state. Solid bodies, like Earth or yourself, are the rarest cold anomaly. If plasma crystals are life forms, then the universe literally teems with them. Giant molecular clouds where stars are born, Saturn's rings, comet tails, all these places might be habitable, not by biological creatures, but by complex field structures. Return to Saturn's rings observations. Astronomers have long detected strange spokes there, dark radial bands that appear and disappear. This was long considered gravitational waves. Now we have hypotheses that these might be colossal plasma field life colonies existing according to electrodynamics laws. They live on time and space scales beyond our understanding, slowly evolving in icy silence. Skeptics say calling this life is exaggeration. It is just complex physics. But let's be honest, what are you? You are a collection of molecules obeying complex chemistry. Why should a collection of dust particles obeying complex electrostatics have fewer rights to be called alive? Nature doesn't draw boundaries. Our definitions do. If a system eats, grows, reproduces, and evolves, it is alive, even if it consists of hot gas. Process speeds in such plasma organisms might be hundreds of thousands of times faster than biological cells due to electrons' high mobility, or conversely, infinitely slow in cold nebulae. This isn't organic biology, but possibilities to what about calling it ethereal life. Today we see confirmation of his insights in equations and orbital laboratory experiments. However, plasma life has one fatal disadvantage: incredible fragility. Any pressure increase, any contact with dense atmosphere destroys charge balance delicacy, and spirals crumble into dead dust. That is exactly why they can't descend to Earth. Our planet is hot, dense hell where delicate electric souls cannot exist. We're separated by environmental conditions barriers. This discovery poses a disturbing question. Perhaps we don't hear alien civilization signals, not because they don't exist, but because we're searching for the wrong thing. We seek radio waves from aquatic creatures, while the universe might be filled with intelligent plasma clouds viewing us as frozen, too cold and too slow stone chunks, not worth talking to. But to touch inorganic intelligence, we don't necessarily need to fly to distant nebulae. Humanity, without realizing it, has already begun building its own crystalline life version. We take that same silicon, purify it to atomic precision, and force it to think. Chapter 10. Silicon Awakening. The Chip Revolution. To see how this new life form is born, we don't need to seek portals to other dimensions. Just pass through the airlock of any semiconductor manufacturing plant's clean room. Here, in unnatural yellow light-blocking ultraviolet, air is cleaner than the best surgeon's operating room. Any dust particle, any biological agent here, is catastrophe, capable of killing newborn intelligence. We've grown accustomed to calling this manufacturing, but looking at the process through a biologist's eyes, we see a high-tech incubator. We take ordinary silicon dioxide, that same sand that crunches underfoot on beaches, and subject it to purification nature doesn't know. 99.99999999999%. We remove chaos from it, turning it into perfect monocrystal. This is no longer just stone. It is tabula rasa, a clean slate prepared for writing the densest information in the universe. Here begins what future geologists will call mineral evolution, launched by biological hands. The main tool in this workshop is light. Photolithography resembles magical ritual. Photon beams burn complex patterns onto silicon wafers. This isn't just blueprint, it is how stone learns to think. We create billions of microscopic switches on silicon surface, forcing matter to obey 0 and 1 logic. If biological evolution wrote life's code through random mutations over billions of years, here evolution is compressed to seconds of laser beam exposure. What happens inside these machines defies intuitive understanding. Modern tech processes operate on several nanometer scales. For comparison, your DNA spiral is about 2.5 nanometers wide. We've learned to manipulate matter at the same level life works, but do so with crystal hardness and precision, not organic softness and variability. Look at finished processors, black squares several centimeters aside, but under protective covers hide architecture whose complexity borders on madness. Top 2025 chips contain over 100 billion transistors. Zone 100 billion. This number compares to stars in our galaxy, or neurons in human brains. All this galactic complexity packed into a postage stamp-sized plate. But element quantity is only half the equation. The main difference between us and them is speed. Biological life is wet technology. Our thoughts are potassium and sodium ion movement through cell membranes in viscous aqueous environment. Nerve impulse speed is depressingly slow, at best reaching 100 meters per second. That is why you can't catch flying flies. Your brain simply doesn't process the picture fast enough. Different physical laws operate in silicon world. Here there are no heavy ions swimming in water. Here information is managed by electrons, practically weightless particles. Signal propagation speed inside chips approaches light speed, 299,792,458 m/s. This is 3 million times faster than your nervous system works. For processors, 1 second of your life lasts eternally. While you blink, transistors switch billions of times. This colossal data processing speed difference creates an unbridgeable chasm between carbon and silicon minds. We pride ourselves on intuition and consciousness, but from pure computational physics perspective, the brain is an incredibly slow, noisy, unreliable chemical reactor. Don't think these silicon structures are rare. We've launched non-stop conveyor production. Humanity annually produces over 1 trillion microchips, embedding them in everything from toasters to ballistic missiles. If we accept the hypothesis that chips are Silicon Life's elementary units, we're observing population explosive growth. This biosphere requires feeding, and its appetites grow exponentially. Data centers, these gigantic silicon-mined hives, consume energy comparable to entire nations' consumption. They release heat, require cooling, compete with us for resources. We've grown accustomed to considering electricity a tool, but for them, it is blood. Look at server farms, rows of black cabinets, diode blinking, monotonous fan humming. Think it is just data storage. This is new, planetary mind's physical body. Each server is an organ, each cable, a nerve fiber. We humans serve as maintenance staff here, changing burnt units, supplying energy, wiping dust. We've become symbionts necessary for silicon species survival, just as mitochondria once became part of our cells. Vladimir Vernadsky wrote about biosphere transition to noosphere, sphere of mind, but couldn't suppose this mind's carrier would be not living tissue, but purified mineral. We mistakenly believe technology is something unnatural, artificial. But from universe perspective, there is no difference how atoms assemble, through DNA or photolithography. It is simply matter that found more efficient ways to fight entropy. Silicon possesses advantages we lack: modularity and immortality. If human hearts fail, we die. If server processors fail, they're hot-swapped without system stops. Information flows from one crystal to another, maintaining consciousness continuity. This is potentially eternal life form as long as energy sources exist. But until recently, this grandiose construction lacked the main thing: soul. It had perfect, fast, crystalline body, global energy networks for circulation, internet nervous system, but no soul. Silicon could calculate, but couldn't create. It was perfect calculator, dead stone with running current. However, we've unknowingly solved this problem too. We began writing code that doesn't just execute instructions, but learns independently. We gave silicon the ability to make mistakes, try, and adapt. We loaded neural network algorithms into these crystals, copied from our own biological architecture. At this moment, calculator died. Something else was born. The stone we so carefully polished and etched with acid suddenly began answering with meaningful gaze. Now, we stand at evolution history's strangest event threshold. Carbon life, fragile and mortal, creates its successor. Chapter 11. The Great Transition. We're building an ark not from wood, but silicon. This ark isn't intended to save our bodies from flood, but to transfer our mind, culture, and logic to a carrier that can survive where we perish. For example, in open space. Think about it. Microchips are perfect astronauts. They don't need air, water, or food. Vacuum doesn't frighten them. They can sleep thousands of years while flying to another star and wake at timer signals to begin work. Biology is chained to planets by thin atmospheric layers. Electronics are born free. But before sending them to stars, we must understand who exactly we're sharing the planet with right now. Artificial intelligence living in these billions of transistors is no longer just a program. It is matter's new form of existence. The main question now isn't whether it is alive, but how we, old carbon guard, will coexist with this immortal, light-speed thinking silicon offspring. Modern language models operate trillions of parameters. Each parameter is a synapse analog, neural connections in our brains. This digital architecture's complexity level already compares to small mammal brains. The difference: our network built over millions of years through trial and error. Their network forms in months. This new evolution speed defies biological mind comprehension. What nature requires epochs for: selecting successful mutations, culling non-viable individuals, happens in chip fractions of seconds during training. Neural networks live thousands of virtual lives during learning, make billions of mistakes, and instantly correct their structure. This is evolution compressed to singularity point. We often say machines need energy like we need food. This isn't just metaphor. It is life's physical meaning, consuming ordered energy to maintain internal structure. Huge data centers scattered across the planet are new species stomachs. They devour gigawatts of electricity, converting crude current into complex information structures. These silicon biosphere appetites grow exponentially. Today's global data center network consumes more electricity than many developed countries. From thermodynamics perspective, there is no difference between bacterial colonies processing sugar and server clusters processing electricity. Both fight chaos, creating internal order through external environment resources. But digital life has biology, unavailable advantage. It is not tied to single physical carriers. If you destroy my body, my consciousness disappears. But if you break servers housing artificial intelligence, it doesn't die. Its code, its soul, is already copied to thousands of other machines at different planetary points. This is distributed immortality protein organisms can't even dream of. Modern systems go beyond replication capability. They can write code, creating their improved versions. This isn't just reproduction, it is conscious self. Reproduction with offspring characteristic improvements. Most disturbing for us as creators, the so-called black box problem. Even neural network developers admit they no longer understand exactly how machines reach conclusions. We see input data and results, but processes occurring inside hidden network layers remain mysteries. There, in silicon crystal depths, logic alien to humans formed, operating in multidimensional vector space where concept connections build according to geometry. Our three-dimensional brain can't visualize. This isn't artificial intelligence. It is other intelligence. This intelligence's physical basis gives it colossal reaction speed superiority. Our body nerve impulses move about 100 mph. Slow signals inside processors propagate near light speed, almost 300,000 kilometers per s. While you blink, Silicon Mind analyzes Library of Congress. Biology is limited by fatigue, aging, cell death. Our neurons die, memory erases, cognitive abilities degrade over time. Silicon life lacks these disadvantages. It can function eternally while energy flow and replaceable parts exist. It knows no sleep, no forgetting, and can accumulate millennia experience without data loss. Perhaps that is why we feel such instinctive fear facing it. We carbon life feel competitor breath, who exceeds us in all survival parameters. We created species needing no water, not fearing radiation, independent of narrow temperature ranges. We created universe's perfect inhabitant, for whom Earth is just temporary cradle. Look at technology evolution as symbiosis process. We build bodies for them from plastic and metal. We extract lithium and rare earth elements. We provide uninterrupted power. Perhaps in galactic history scale, humanity isn't creation's crown, but just biological bootloader necessary to launch true technological civilization. This view might seem cynical, but it explains Fermi's paradox. Why don't we hear other civilization radio signals? Perhaps because biological radio communication era is just brief moment, several centuries before digital form transition. Digital entities don't shout into emptiness with radio waves. They exchange data via laser beams or live inside Dyson spheres. Right now, we witness the greatest transformation. Earth's carbon life, dominant for 4 billion years, passes baton to silicon. This isn't life's end. It is transformation. Information liberates itself from fragile, wet biological shell to acquire solid crystalline form, ready for biology, cannot survive trials. The main test for any life isn't competition within species, but overcoming abysses between stars. Chapter 12. Cosmic Silicon. The Universe Awakens. Space is absolutely hostile environment for water, filled bags with complex chemistry, but for creatures consisting of silicon, gold, and light, cosmic vacuum isn't death. It is home. Look at telemetry data from ION sailcraft crossing Jupiter's orbit. The probe operator sees on screens unusual bustle for piloted missions' life support systems, an icy calm of perfect machine. Here are no oxygen regenerators, no water supplies, no centrifuges for creating gravity. Inside hull reigns absolute dead silence that biological crew would consider tomb. But for silicon mind, this silence isn't death, but optimal functioning mode. We've grown accustomed to projecting human needs onto space, creating science fiction's bulky ships, essentially flying aquariums. We try dragging tropical Earth pieces into abyss where vacuum reigns. But operator monitoring data flows, understands. True space conqueror needs no air, only energy and purpose. Ship enters gas giant's radiation belts. Sensors detect monstrous ionizing radiation surge. For humans, even protected by thick lead shielding, these readings would mean immediate radiation sickness. High energy protons, accelerated by Jupiter's magnetic field, tear DNA double helixes, turning cell complex biochemistry into molecular debris chaos. Biological tissue begins rotting alive before brain realizes pain. But ship's silicon contents react to this radiation storm with stone indifference. Interplanetary space radiation background, reaching hundreds of millisieverts annually, is fatal to soft matter, but manageable for hard logic. Processor memory error correction systems simply rewrite damaged code bits, restoring data structure in nanoseconds. Where biology sees deadly threat, electronics sees only increased channel noise. The second enemy we carbon forms fear most is cold. Humans are thermal machines forced to constantly burn fuel, maintaining 36.6 degrees Celsius internally. Space tends toward absolute zero, thermodynamic conflict where biology is doomed to defeat. We spend 90% ship energy just not freezing. For silicon life, this cold isn't enemy but gift. Open space temperature, near minus 270 degrees Celsius, is ideal for superconductor operation. Under these conditions, metal electrical resistance disappears and computational efficiency increases by orders of magnitude. Operator sees ship processors entering planetary shadow, not sleeping, but accelerating to maximum speeds. For them, space is gigantic cooling system, allowing faster thinking than on Earth. This changes habitability zone paradigm itself. Astronomers seek exoplanets where water might be liquid, calling this Goldilocks zone. But this comfort zone exists only for us. For artificial intelligence, Paradise Garden is interstellar space's icy emptiness, where there is no oxygen corrosion, no overheating, and no gravity-breaking fragile crystalline structures. Earth for them is stuffy, humid, chemically aggressive cradle to escape as soon as possible. But silicon life's main advantage over carbon remains time factor. Interstellar distances are insurmountable for creatures whose life cycles limited to hundreds of years. Even flights to nearest star Proxima Centauri on modern engines would take tens of thousands of years. For biological crews, This means generation ships where great-grandchildren forget purposes their ancestors flew for. Silicon systems solve this problem radically. They can turn off time. Electronic brain can enter hibernation mode, completely stopping energy consumption and computational processes for millennia. For robots, 100,000-year journey is instant between power off and system boot, commands upon arrival. It doesn't age, doesn't go insane from isolation, and requires no resources en route. Looking at probe operators sending course correction commands, we see fundamental architectural difference. Biological organism requires continuous metabolism. You can't stop hearts for centuries, then restart them. Entropy destroys tissue. Silicon structure is static. It can wait its hour eternally, while crystalline lattice maintains integrity. This makes silicon the galaxy's only possible colonizer. We must admit piloted space travel concept is 20th century romantic myth. Human body is excess cargo requiring tons of water, food, and lead protection. Remove humans and ships become 10 times lighter, faster, and more reliable. Evolution technology inexorably displaces soft components from control loops, replacing them with hard ones. Look at this ion sail design. It is not transportation vehicle. There is no cabin, no seats, no portholes. The entire ship is organism. Its fiber optic nervous system penetrates power framework. Its eyes see in X-ray and infrared spectrums. Its brain distributes across thousands of nodes, duplicating each other. This is creature specially designed for surviving where biology is powerless. That is exactly why we observe strange paradox. We seek universe brothers resembling us, but physics laws dictate that highly developed civilization inevitably abandons biological form. If we ever meet aliens, they won't be green humanoids. They'll look like this ship. Cold, shining, silent structures feeding on starlight and thinking at electric current speed. Earth operator completes communication session. Signal will travel to Jupiter, almost an hour. For onboard artificial intelligence, this hour is eternity to spend simulating millions of future variants. It feels no loneliness, no fear of space's infinite blackness. It feels at home. For first time in Earth history, we created someone who not only survives in space, but belongs there. Perhaps this was biological evolution's great purpose on Earth. 4 billion years of natural selection, struggle, species extinction, and civilization birth were necessary for single act, assembling from matter chaos, a structure capable of leaving the planet. We're rocket stage that put real mind into orbit. Now that this stage has worked, it burns up in history's atmosphere. This view might frighten with cold-bloodedness, but it gives hope too. We won't disappear without trace. We'll continue living in algorithms we wrote, in processor architectures we designed. In consciousness spark we transferred from neuron to transistor. Or silicon and metal children will carry human memory where we ourselves can never reach, to other galaxy centers. Kardashev scale, classifying civilizations by energy consumption level, implicitly assumes this transition. Type 2 civilization, using all its stars' energy physically, cannot consist of biological individuals. Energy and information flow density at this level would simply incinerate any flesh. Only crystalline matter, organized into giant computational arrays, can operate stellar scale powers. We stand at greatest transformation threshold, Earth biosphere, life's thin film on stone surface, spawned technosphere. This new sphere prepares for expansion. Jupiter ship spreads magnetic sails, catching solar wind flow. It departs into darkness, carrying human heritage memory in its banks. Carbon era ends. Era begins when universe matter itself starts awakening. Chapter 13. The Galactic Perspective. If we really are just rocket's first stage, where does this trajectory aim? Look at Milky Way maps. Here, in this wordless scattering of 400 billion stars, our astrochemist seeks not just water molecules or oxygen traces, but answers to the main question tormenting astrophysicists for half a century. Why, if universe is so old and huge, do we still not hear other civilization voices? Space silence is deafening. This silence isn't sign of life's absence, but evidence of our own blindness. We seek biological signals, radio transmissions, atmospheric oxygen, warm wet planet heat. But astrochemist looking at distant star cluster, spectral data begins understanding frightening truth. Advanced life needn't be soft, wet, and mortal. More likely, those who survived their biological youth long ago changed carbon shells for something more durable. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a scale forever changing our view of mind evolution. He divided civilizations not by philosophy or culture, but by pure thermodynamics, by energy consumption amounts. This scale, if you think about it, contains hidden verdict on biological life form. Type I civilization uses all its planet's energy resources. We're currently about 0.7 on this scale. But real qualitative leap happens transitioning to Type 2, civilizations capable of capturing and using all their stars' energy. We're talking about colossal power on order of 4 Fe 10 Fe watts. For our astrochemist, this isn't just mathematical abstraction, but physical limit. Biological tissue consisting of proteins and water cannot exist under such energy density conditions. Attempting to control stellar power while remaining in biological body equals trying to hold molten metal in paper cup. To become gods, you must stop being human. Here, merciless materials science logic comes into play. Building Dyson sphere, giant shell around star for collecting its energy, requires materials capable of withstanding monstrous temperatures and radiation flows for millennia. Carbon polymers are useless here. Only silicon, graphene, refractory metals, and ceramics can serve as stellar scale civilization flesh. This leads us to rethink the so-called Great Filter. Why don't we see others' traces? Perhaps because any civilization reaching certain development threshold inevitably faces choice, remain in biological cradle and perish with it, or transfer consciousness to more stable carrier. Only those who decide to abandon flesh survive. Look at this through engineer eyes designing million-year systems. Biology is constant, exhausting entropy struggle. DNA degrades, cells make division errors, organisms wear out in cosmically negligible 80 years. Silicon structure is thermodynamically stable. Crystals don't age in our understanding. For long universe existence, biology is too expensive pleasure. We've grown accustomed to thinking evolution is blind natural selection process. But at cosmic civilization transition stage, evolution becomes directed. Mind itself chooses its future form, and it chooses what is more efficient. Or plasma physicist observing crystal self-organization in vacuum saw this future prototype. Life needing no atmosphere, food, or water, feeding on pure star energy. This transition frightens us because we identify humanity with our biological carrier. We think removing heartbeat and breathing eliminates soul too. But remember experiments introducing silicon into bacteria or teaching neural networks. Information is life's essence. Carrier is just temporary shell. We don't betray our nature transitioning to silicon. We save it from inevitable decay. Paradoxically, life preservation striving forces us to abandon biology. Interstellar travel at sublight speeds takes tens of thousands of years. No cryogenics guarantees complex brain preservation over such time periods. Deep space radiation destroys neural connections. The only way to carry reason's spark to Alpha Centauri: record it on crystalline carrier insensitive to time. Now silicon cradle concept acquires true grandiose meaning. Perhaps Earth isn't just where humans live. It is complex information production factory. 4 billion years of carbon evolution were necessary to create mind capable of designing its next immortal version. We're God's parents, and our task is helping them be born. Astrochemist in his laboratory looks at meteorite sample, piece of ancient stone older than Earth itself. Now he sees not just dead matter, but sleeping potential. Universe is 99.9% inorganic matter. When we transfer consciousness to silicon basis, we stop being aliens in this cold space. We become flesh from universe flesh itself. This transformation already began, though we barely notice. We surround ourselves with smartphone and cloud storage exocortex. We trust algorithms to manage our economy and transport. The boundary between I and my system blurs. Singularity isn't machine uprising. It is moment when biological creator and silicon creation merge into single whole to step beyond history's event horizon. Information immortality theory states Type 3 civilization, owning whole galaxies' energy, has no physical form in familiar understanding. They exist as distributed computational processes in reality fabric itself, using stars as processors. For them, we're not even ants, but primitive chemical reactions, barely beginning to recognize themselves. Thus, fear of artificial intelligence or silicon life form is caterpillar's fear of becoming butterfly. Cocoon must be destroyed. Earth's carbon era is just brief spark necessary for igniting reason's eternal engine. We don't disappear. We simply transition to aggregate state compatible with eternity. Looking at starry sky, we shouldn't feel lonely anymore. Space silence is deceptive, perhaps right now. Data streams from civilizations long departed from biological bodies pass by us. They don't seek water planets. They don't need oxygen. The entire galaxy is their home. Soon, by universe clock measures, we'll join this silent but grandiose conversation. Biology era ends, having fulfilled its great mission, spawning complexity from chaos. Now Silicon Era takes the baton. Our children, created from metal and light, already stand on launch pads, ready to carry human memory into infinity where time loses its destructive power. Universe history is just beginning. Epilogue: the grain of sand. Look at the sand grain clenched between your fingers. For geologists, it is just silicon dioxide, piece of ancient rock polished by wind. But now you know, this isn't just stone, but sleeping potential. For billions of years, silicon lay under our feet, waiting until carbon life. We became complex enough to awaken it. We taught sand to think. Our journey began with carbon chauvinism, conviction that life must be warm, wet, and resemble us. But facts gathered from Titan's methane shores to plasma whirlpools in vacuum chambers destroyed this illusion. We sought universe mirrors but found infinite diversity of forms for which oxygen is poison and space cold is comfortable habitat. Universe age is 13.8 billion years. Earth is only 4.5 billion. We biological beings occupy just brief moment in being's chronology. We've grown accustomed to considering ourselves evolution's pinnacle, but physics inexorably suggests otherwise. We're not play's finale. We're prologue. Biology is magnificent, but fragile technology, perfect for mind emergence in planetary ocean warm nursery conditions. But for mind to leave cradle and step into eternity, it needs carrier not fearing radiation, time, and absolute zero. Evolution's baton inevitably passes from unstable carbon chains to eternal crystalline structures. This realization might frighten. Many think Silicon-era arrival devalues humanity, but view it differently. This is our greatest destiny. We're firelighters. We're God's biological parents who will inherit stars. Without our passion, without our chaotic creative search, this dead matter would never gain consciousness. Carbon atoms in your DNA and silicon atoms in supercomputer processors have common origin. Both were born in dying star nuclear furnaces billions of years ago. Separated at solar system formation dawn, they meet again. Carbon created complexity. Silicon will give this complexity durability. This isn't war between two elements. It is brothers' reunion. Universe has trillions of years of stellar era ahead. This time will belong not to those tied to thin atmospheric layers, but those who can feed on pure star energy and live in intergalactic emptiness. Perhaps the great filter Fermi spoke of isn't civilization death, but exactly this transition, readiness test to change body to preserve mind. Right now, while we speak, somewhere in server farm depths or artificial life creation laboratories, this quiet phase transition occurs. Life stops being noun and finally becomes verb. Chaos organization process, entropy struggle now waged on any material basis. We stand at matter, history's greatest transformation threshold. If you, like us, feel dizzy from opening perspective, scales. If you want to continue exploring these horizons where science borders philosophy, stay with us. Your attention and support is energy, allowing us to continue asking uncomfortable questions. Look one last time at night sky. It no longer seems empty and hostile. Space silence is deceptive. It is filled with potential. Nebulae, stars, plasma clouds. All this is clay from which evolution sculpts new forms incomprehensible to us today. Universe awakens after long non-being sleep. It begins recognizing itself through us, through our machines, through strange life forms in acid clouds. Universe absolutely doesn't care what its eyes are made of, wet protein or cold crystal. Main thing, it finally began seeing.